Right, let's continue with part 2 of the infrared spectroscopy. So now let me go back to my tablet. All right, so earlier I mentioned about energy. So light, about light. Oops, about light. Light, and then can be expressed in 3 ways. Can be in wavelength or frequency or wave numbers. So, but the relationship you probably remember from the um, physics or something along the line that energy is related in terms of the something called um, energy is related to to frequency and wavelength. So something like this. So h nu, something like that, and this h nu. So by the way, this is by the way nu in Greek letter. So it looks like a V, but in reality, I mean like it's it's a nu. Means that it's it's a frequency. Uh, and so and and this is what we call the Planck's constant. I think this might be C. Then let's rewrite this. Here we go. So Planck's constant. And you don't have to remember, for this class, you don't have to remember what the Planck's constant is. I'll give it to you. So in the equation sheet, you will get what the Planck's constant is, but basically Planck's constant is like 6.63. So again, you don't have to memorize it. 6.63 times 10 to the minus 34th joules times second, something along that line. And then so it's a frequency. So now energy and so light is an energy. Energy and these parameters, the wavelength, frequency, all these 3 things are related. So they're related. So now, how are they related is the question. Now, in terms of equation, energy is related to frequency with E is equal to h nu. But remember, nu is equal to, well, the nu is what? It's a frequency and it's light. So turns out that oops, I lost my screen. So here we go. Wait, where did it go? All right, so here we go. So so nu is a frequency. So so where was I now? So the speed of light, right? Speed of light. Oh, by the way, c is the speed of light. Is related with let's see, h shoot, I should have probably wrote it this way. C, speed of light is equal to wavelength times the frequency. So that's the relationship between speed of light. So this is a relationship between speed of light and then wavelength and frequency. So of course, c, the speed of light, is related with frequency and wavelength. So if you have wavelength and frequency, and now you know that E is equal to h nu, but then nu, if you rewrite this, nu is equal to c over lambda, if you rewrite this equation algebraically, then you can substitute this into here. So in this case, you have E is equal to h times c over lambda. So you can rewrite this as, let me rewrite this, E is equal to hc divided by lambda. Okay, fine. So why do we care about this? So let's say you have a 400 nanometers of light. So but you don't know the frequency, or you didn't know the frequency. So how much energy? So now question is, how much energy? So let's say, how much energy is in 400? I'm going to put a bar here just so that we can get 3 sig figs, 400 nanometer light. Then in this case, h is equal to 6.63 times 10 to the minus 34 joules times second. And then c, speed of light, which is constant, again, it's 2.998 times 10 to the 8th meters per second. Again, this constant, 2.998 times 10 to the 8th meters per second, I'll give it to you. All right. This doesn't look great, so let me rewrite this. So it's 2.998, okay, and divided by 400 nanometers. But you have to be careful. In this case, the unit in this case is in meters. Remember, so unit is in meters. So nanometer has to be converted. So 400 nanometers light. So I'm going to just do a unit conversion. So 10 to the 9th, well, minus 9th, well, let's see, 10 to the 9th meters. Let's rewrite this because it's in the denominator, so it doesn't look clean. So I'm going to rewrite this a little bit. So I'm going to move this a little bit. Doesn't look great. So I'm just going to move this. Here you go. Of course, it didn't catch everything. So let's redo this. Let's hopefully I can capture everything here. All right, and then I'm going to move this down a little bit so that it looks cleaner. So now I have a little bit more space. So 1 times 10 to the 9th nanometers is equal to 1 meter. So again, because it's, it's 10 to the 9th nanometer is equal to 1 meter. Or you can call it 10 to the minus 9th meter is equal to 1 nanometer. It's the same thing. But anyways, so I'm just going to use the conversion factor here to the 9th nanometer. So nanometer cancels out. So, and then meter and meter would cancel out. And then, oh, by the way, it's the per second, and second cancels out. So at the end, you'll only have joules in this case. So your answer will be in joules. So it's equal to, and then if you plug that in, it's like 4.9 something, 4.9, probably 6 something, 4.967 or something, times 10 to the minus 19th joules. Joules. But remember, so in this case, you have 4 digits here. So, well, sorry, you have 3 digits here, looks like. In terms of sig figs, you have 3 digits here. And then you have 4 digits here. So at the end, you end up having 3 digits. So you have 4.97 times 10 to the minus 19 joules is your final answer. So keep that in mind. Okay, so that's how to do the energy calculation. So far, so good. All right. So I'm going to just move along. So energy calculation. So why do we care about the energy calculation? This is, changing wavelength into the wavelength into energy. So remember, energy, um, energy, and energy and frequency and wave numbers are all related. So remember that if you have wavelength going from here to like let's see, going from here to like this, let's say, so wave like a sine wave like this. So then, so the longer the wavelength, the longer the wavelength, longer the wavelength, lower the energy. Because remember, IR is like, it has 700 nanometers, so it's like, so moving like this. Whereas 400 nanometers UV light would be, the wavelengths would be shorter. So imagine that the light particle is moving like, like this. So, you have long wavelength and short wavelength. Within the 1 second interval, I could move like this within 1 second or 1 second, right? So which means it's moving like this. The shorter the wavelength, I mean, visually speaking, it looks like it has more energy, right? I mean, so keep that in mind. It's sort of intuitive to see it like this, but shorter the wavelength, the higher the energy, but it's not convenient. But higher the frequency, by the way. So which means shorter the wavelength, which means you have to still move the same distance within the 1 second interval, let's say in this case. So higher the frequency, higher the energy, which is fine. But the frequency, frequency is not intuitive for us to think in terms of like about light, to deal with light. So something alternative unit was sought, and that happened to be the wave numbers. So wave numbers. So what is wave numbers? Wave number is the wavelength, right, in centimeter, and then to the minus first is what the how it's handled. So let's say 400 nanometer light, and then you convert this into centimeters. So let's make that into 3 digits. So then you have 1 times 10 to the 9th nanometer is equal to 1 meter, and then times 1 meter is equal to 100 centimeter. So if you solve this, then you end up having what? 4.00 times 10 to the, what is it? Minus 5 centimeters. And then, so wave numbers in this case, so wave numbers would be, at 400 nanometer is equal to, so it's 1 over 4.00 times 10 to the minus 5 centimeters is equal to, in this case, 25,000 wave numbers. Of course, in this case, sig figs would be 3 digits, so you would have a bar here. So keep that in mind. So, this is so why do we care? Going back to this, higher the frequency, higher the energy. It's it's not an inverse relationship, like longer the wavelength, the lower the energy. It's not intuitive. All right, so this one, right, not intuitive. And this one, the frequency, higher the frequency, higher the energy, not intuitive either. But remember, in this case, wave numbers. So, higher the wave numbers, higher the energy. So this is pretty convenient. So that's what is used in infrared spectroscopy. So keep that in mind. So now that said, so infrared. So if you have the infrared spectrum, you'd see wave numbers, and then this side happens to be, I don't know, 3,000 wave numbers. This side happens to be like 500 wave numbers. So then you have, or you can do either way, but and then you have something called either transmittance or absorbance, depending on how the graph or how the spectrum is taken. But anyways, so if you have let's say you have an object, let's say, and then you fill with the object with a certain color. Let's say I'm just going to use red. And then if you shine a light, so I'm just going to put H nu, which is basically means light. It's a chemist lingo for H nu is like chemist lingo for like light. So I'm just going to put light. And then some of the light is being absorbed, and some of the light comes out. Some light is absorbed, right? So some light is absorbed, then this energy has to go somewhere, and energy is used to vibrate the molecule, and this vibration is the energy is used to vibrate the molecule that specifically match with the functional group being present in the molecule. So in the next video, I'm going to talk about the actual vibration. So now, again, if you can continue, that's great, but then I'm going to stop the video here, and then I'll see you next time. Watch.